This is a Thorium Energy Alliance Conference. So it has thorium in the name, and you would think that we would be talking about thorium all the time. But think about all the talks that have been here. It's mostly about uranium, right? That suck. We should be talking about thorium because thorium can do something unique and special that uranium cannot do. And I've been pissed off by so many conferences that call it like advanced reactors or whatever when it's not. It's like light water reactors. And I really think we should try to have a conference, for example, this one, where we sort of look into the future and not into the past. And so part of my talk today is about why I think thorium is special. And I know many of you know this already, but I hope some of my slides will give you courage to talk differently to your neighbors and friends and colleagues. So I think many of us got excited about an image like this, where the ball the size of the golf ball can supply you with all the energy you need for your entire life. Not just electricity, but everything, transportation, all the products you need, all your share of all the public, like roads and houses and hospitals, everything. It's amazing that you can get all that energy out of this little ball. And it costs only less than $100. So if you live for 100 years, it's $1 per year. That is amazing. And that's why I think most of the people in this room are here. But the problem is we don't have the machine that can take the energy out of that ball. And that's what we're trying to build. And I know a few others who are trying the same. And hopefully, within a few years, it will happen. And I think we should all celebrate that like crazy. We've been at this for quite a while now. So thorium, not only does it have unique properties in terms of being able to produce a huge amount of energy, but there's also lots of thorium. And a lot of times when you talk to uranium people, they say, oh, there's 3 or 4 times more thorium than there is uranium, which is technically true, but all the uranium reactors I know, they run on uranium-235. And you know that little sliver, that orange little sliver there? That's uranium-235. It's very rare, and you can't really use it. You have to enrich it and everything. So in reality, there's 1,000 times more thorium than there is uranium available to us. I mean, you can always debate about uranium in seawater and all that, but thorium is just a lot easier to get to. One thing that proves that is we already do mining for other materials, and we get thorium out of the ground when we do mining for rare earth and gold and copper and shit. And that thorium alone that we already get out of the ground today would be enough to power the entire electricity of the whole planet. We don't need to open one additional mine. So that is also amazing, and you can't say that about uranium. I mean, now they said at COP28 we need 3 times more uranium, and everybody's scratching their head. Where's that going to come from? And what about enrichment facilities and what is it called, like fuel production and everything? And of course, the uranium price already went up just because they start talking about it. A lot of times when you talk to sort of the people from the general public, they will tell you that nuclear, it's too expensive, it takes too long to build, it has this awful waste, and it's dangerous. I hope some of my slides today can sort of help you tell them what you think. I agree that classical nuclear is too expensive and too slow. No doubt about it. It sucks. But I think we should try to sort of rethink what can we do about that. How can we solve that problem that it's too slow and too expensive? I offer some ideas today, and I hope we can have more discussions over a beer later. Then people say it's dangerous. That's definitely a hoax. I mean, nuclear is not dangerous. I'll get back to that in some of my slides later. And then they say, oh, there's all this awful waste. Yeah, it is not the best waste, I agree, but maybe we can do something about it. I mean, let's try to look at it in a positive light. Then there's these guys that says, oh, there's these new reactors, small modular reactors, advanced modular reactors, generation 4. There's even people talking about generation 5 now. Molten salt reactors, high temperature reactors, all this crap. It doesn't change anything. It's still the old stuff that we've had for, I don't know, 7 decades. So please, when you talk to your neighbor or your colleague about Copenhagen Atomics, please don't call us a small modular reactor or an advanced reactor, generation 4 or 5 or whatever. We are something completely different from all these other. Okay, so I'll try to sort of give you some ideas of how you can talk about the difference between uranium and thorium. So here is a list of properties, you could say, for solid fuel reactors. It's sort of, I want you to go home. Don't trust me. Go home and look this up for yourself. This is sort of the average numbers for a solid fuel reactor. You know, those designs, they last for 60 years maybe with extensions. You can look up the uranium price on the web. Right now it's at 4,500 for 5% rich uranium. In those type of reactors, you can get 1 to 2 gigawatt hours out of every kilogram of fuel. Some reactor designs are a little bit better than others, but that's sort of the average for solid fuel reactors. And you know that most of them take between 4 and 15 years to build. I mean, maybe one is a little bit faster and definitely some are a little bit slower, but that's sort of the average. And the price of electricity from solid fuel reactors are between $60 and $120 per megawatt hour electric. So how does that compare to thorium, do you think? Do you think thorium is the same, sort of roughly the same ballgame? A few people are shaking their head. Most of you are just holding your breath. So I had to compare it to Copenhagen Atomics. And again, some of these numbers you cannot look up. But let's talk about it. So our design is also sort of 50-year lifetime, plus maybe extensions. The price for thorium is $50 per kilogram. We've already ordered tons of thorium, so I know this price because that's what we paid for it. Of course, just like uranium, the price might go up or down, but since there's so much thorium in the world, I think it's more likely to go down than to go up in the future. If 1 kilogram of thorium, you can get 22 gigawatt hours of energy out of that, thermal energy. And then how fast can we build this? Well, I've also been at some of the previous conferences, and the goal for Copenhagen Atomics is to build 1 reactor every day. But of course, we also need to deploy them, and deployment is a little bit more difficult. So I would expect that in the beginning, for a 1 gigawatt power plant, it would take 18 months to deploy that. And later on, when we sort of get things up to speed, we should be able to deploy in 6 months a 1 gigawatt power plant, because it's not built on site. It's truly modular. It arrives on trucks. And then the price of energy for these type of reactors is between $20 and $40 per megawatt hour. So again, completely different ballgame. And I've made sort of a column with the differences so you don't have to do the calculation in your head. You can see on most of these things, we are an order of magnitude better than solid fuel reactors. And so I don't think we should compare ourselves to all the old reactors. I believe that our reactor is like a jet airplane, and the old reactors is like a horse carriage. It's not the same thing. Yeah, so we want to mass manufacture these reactors, and we planned this through the whole development of our reactor, the way we planned the whole company. We want to make 1 reactor every day. You know that car factories, they can easily make 1,000 cars every day. Our reactors have less components than a modern car. So of course we can easily assemble 1 reactor every day. I mean, we don't start in the morning and finish in the evening. We have sort of an assembly line, and the reactors move down the assembly line, and then they come out at the end. 1 comes out every day. The problem is not so much to mass manufacture these. The problem is to deploy 1 reactor every day. That's a difficult challenge to get approvals to deploy 1 reactor every day. And we're working on that. I'd love to spend some more time on that, but I have limited time, so I've decided to do that some other year. But there's one more thing I want to point to, is you guys have done physical labor where you dig a hole in the ground or move some things, and you're sweating and you're working really hard. And then you know that you're not as strong as a horse, so you're not doing 1 horsepower. Actually, on average, like an adult man that works really hard, he can do 150 watts of work with our muscles. And you can't work. I mean, you can't work 24 hours. You have to sleep and eat and stuff as well. So if you try to calculate this type of reactor, this reactor can produce 42 megawatts of electric energy, 24/7. So if you try to calculate how many people it would take to do the same amount of work, it's actually amazing. It's more than 1 million people to do the same work. Of course, we don't do that. We buy electrical motors and have them do pumping or whatever. And robots are coming. That's what they say, at least. And those robots will also need electrical energy to work. But think about it. You know, I think this could change the future of how we live and play on this planet. Because if we make one of these reactors every day, some country, let's say some island state somewhere, they call Copenhagen Atomics, say, we want to buy 300 of your reactors. We say, yeah, okay, let's make an agreement, and then we deliver 300 reactors to them. That's the same as having 300 million workers added to your country. That's more than there is of workers in the entire United States. So I think this idea of deployment can really change a lot of countries. Let's see what will happen. All right, I announced that I would talk more about danger and nuclear energy. I heard at least several talks today where they say, "Ooh, this is safer nuclear," and I call bullshit on that. So let's talk about the numbers the way I see the numbers. I mean, you don't have to agree. But I think at least we can have a little bit of fun talking about the numbers in a different view. So I'm sure all of you have seen this before. Coal-fired power plants are the most dangerous type of power plants we have. They kill the most people. I think many of us believe that roughly 1 million people die every year from coal-fired power plants. It's not only from air pollution, it's also from mining and from shipping all that coal and everything. So 1 million people, right? And coal-fired power plant has been going on for many decades. So if you sort of go all the way back to the Second World War and calculate how many people died, it's probably more people than died in the Second World War from coal-fired power plants. So I don't know if you think it's dangerous. So if you have something that can slow down the growth of coal-fired power plants, how can that be dangerous? And nuclear energy, if we look at nuclear energy, it's not very dangerous, like 1,000 times less dangerous than coal-fired power plants. And if you look at those numbers for nuclear energy, then they also include the death from mining. And you know that it's really, really difficult to get a reactor approved because the reactor have to be super duper standard, like really safe. But do you know how much time we spend on making it safe to mine uranium? Not so much. What about when there's an accident? I mean, if you build thousands of something, eventually there is going to be an accident, right? We can't really make 0 accidents. So when there is an accident, and we've had a few accidents, Chernobyl and Fukushima, how many people actually die? I don't know, a few people. A few people in Fukushima, 1 guy. But then when an accident happens, then there are some humans that come in and say, oh, we should do something. Like, for example, in Fukushima, they wanted to have evacuation. More people died from that evacuation than from the reactor itself. So it's not the reactor that is dangerous, it's the people that are dangerous. The people that make wrong decisions. In Chernobyl, it was even worse. You know, when there's an accident and there's iodine, you're supposed to get iodine tablets. And they had the iodine tablets. But there was a guy who decided that they shouldn't give the iodine tablets to the people because it might scare them. And that's the thing that killed the most people in Chernobyl. It's a stupid mistake by 1 guy. Is there any really big regulations around that to avoid that stupid people make stupid mistakes? No, not at all. So the whole, like, trying to make nuclear more safe, it's a hoax. And it's just trying, it's a hoax by, I don't know, anti-nuclear people to try to hold nuclear energy back. And I think we should just stop this. And honestly, when I hear some of you saying that new nuclear or molten salt reactors or small modular reactors is more safe, I think you're doing a disservice to the industry, because what you're really saying is, I want to slow down nuclear and I want to make it more expensive. That's what you're saying. And that's not what we need. And then also, well, I should go to the next slide for that. So there's also this misunderstanding of radioactivity. We hear this again and again, especially if some of us are interviewed by the media. They say, oh, but is your reactor radioactive? Yeah, it is. Oh, then it must be dangerous. Okay, like, what are you talking about? Of course, most of you know electricity, and you probably know that this 1.5 volt battery is not dangerous. And I don't know if you know where you learned that, but I assume that all of you know that 1.5 volt batteries are not dangerous. I also assume that all of you know that high voltage power lines like 1,000 volt or 10,000 volt is dangerous. I mean, if you touch 1,000 volt, you might die. You're not guaranteed to die, but you might die. And it's a little bit similar if there's the kilometers per hour. If you drive 1,000 kilometers an hour in some crazy car, you might die. It's dangerous. But if you drive 100 kilometers an hour, I'm sure many of you have done that, even within the last week. And I don't think you feel it's super dangerous, but I also think you know that it's not risk-free. And of course, it's the same with radiation. I mean, there's levels of radiation that are super dangerous, and there's also levels of radiation that is not dangerous. And so, of course, I should say that there is no physics that makes a connection between voltage and kilometers per hour and radiation. I mean, I made this comparison, but the way I made that comparison is at what level do people die? And when you look at radioactivity, 1 sievert might kill you. It's not super likely, but you might die from 1 sievert. If you get 10 sieverts, it's not good, right? It's like 10,000 kilovolts or whatever. It's not a good idea. But if you get 20 millisieverts, which is the limit for radiation workers, nobody has ever died from that. We don't know any evidence that anybody has ever died from that. So that's the same as a 1.5 volt battery. And, you know, I've never seen anybody spend millions of dollars on making 1.5 volt battery safe. But I've seen people spend millions of dollars on trying to make 20 millisieverts safer. And every time you guys talk about ALARA or LNT or whatever, what you're really talking about is how can we kill more people from coal-fired power plants. Every time there's a meeting about ALARA or LNT or whatever, you know, that delays and makes nuclear energy more expensive. So it's a disservice to the people of this world to try to make nuclear even safer. I mean, there's actually people who live in areas of the world where there's 100 millisieverts. You get 100 millisieverts per year in your house. So they live in that house for their whole life. And there's no statistical evidence that they get more cancer than the rest of us. So 100 millisieverts is a little bit like driving 100 kilometers an hour. I mean, we know that, you know, every now and then there might be a problem, but most of the time it's not dangerous. So yeah, I hope you can use that scale for something. Then I want to talk a little bit about the development plan of Copenhagen Atomics. We've divided our development into these 6 milestones. We started 10 years ago, and the most time we've spent on developing the technology for the first 10 years. We have developed unique pumps for molten salt reactors. We have developed a unique molten salt reactor core. It's called the onion core. It has unparalleled efficiency compared to any other reactor we've ever seen. So that's one of the things we developed. I'll talk about it a little bit later. We've also developed a method to purify salt, because if you purify the salt and get rid of moisture and oxygen and everything, you get less corrosion. And some people say, oh, corrosion is a big problem for molten salt reactors. I think we've solved that. We don't bother to run with expensive materials. We can use stainless steel 316 and run that for many years, no problems with corrosion. So we've spent a lot of time on doing basic development of technology for molten salt reactors. And we are also sharing that with the industry. We're selling some of the technology to other players in the industry. All right, and then the second milestone there is we're developing non-fission prototype. So we've already built 2 reactors, full-scale reactors, the same size as our commercial reactor, and we're running those with non-radioactive materials, so basically FLiNac salt, in our workshop in Copenhagen. So we heat it up with electricity and we pump the salt around, and we do all kinds of tests with thermal expansion and thermal cycling and heat exchangers and all these things we need to test before we can go to a real reactor. And the first real reactors for our development plan is a 1 megawatt test reactor that we plan to run in 2026. So very similar to ACU, what ACU is doing. But the difference is that our reactor has the onion core and it's using thorium as a blanket. So it will be the first thorium molten salt reactor in the world, I think. Let's see. That first test reactor, we're going to run it for 1 month, and we're going to run it at 1 megawatt. So it's basically just a test. And the reason why we run it for a short amount of time and small power is then we can transport the things around on the roads afterwards. We would really like to be able to move it around, especially the fuel. So that's the reason for that. But like I said, it's a full-scale reactor. It's the same reactor design as the commercial reactor. We've just not run it at full power. So as soon as we have that up and running, we will move towards the first commercial reactors. And once we have proven that the commercial reactors are working and they're providing energy and selling energy and they can run for a number of years, then we will start the mass manufacturing sort of in the early 2030s. And I think we will go just directly to making 1 reactor every day. And of course, right now we're trying to get our heads around how do we actually deploy all those reactors. And that's a whole talk by itself. So you will have to wait till maybe next year to hear about that. And then finally, the really, really, really big goal is milestone number 6, where we want to make a thorium breeder reactor in thermal spectrum. That's gonna be cool when we do that. That's 2035. A little bit about our reactor design. So it's I talked about in the beginning that we have this ball out of thorium, and we want to make a machine that can convert it into energy very, very efficiently. And this is sort of a cartoon drawing of what it would look like. If you look inside in the middle there, we have the schematics of an onion core, sort of cut through in a section view. And then right next to that, there's an insulation wall. And that's because inside the 40-foot shipping container, there's a cold region and a hot region. The cold region is sort of blue and it's room temperature. The hot region is a little bit orange and it's usually 600 degrees. And then you have a number of heat exchangers that takes the heat and get the heat that is produced from the hot salt out to the customer. And the heavy water we use as a moderator needs to be cooled all the time. Roughly 5% of the energy that is produced by the reactor goes into heat in the water, and we need to take that out. So there's a number of heat exchangers sending the water out for cooling. And then you could see at the bottom there's a number of tanks. So when we shut down the reactor, all of the liquid up in these heat exchangers and the reactor core will drain into the tanks at the bottom. And basically we do that just by stopping the pumps. As soon as we stop the pumps, everything will drain down into the tanks. And then when we start the pumps again, it will start running. So basically to shut down this reactor, you just cut the power to the box, then it will stop. So it's a very simple mechanism. And you also see the thick line around that, sort of the thick gray line around it. That is the third barrier. So we need 3 barriers between the radioactive salt and people outside. And the third barrier is sort of a very, very thick wall of steel. So 0.5 meter thick steel wall to protect the reactor from what's coming from outside. But also if something happened inside the reactor, it will protect people outside. And 0.5 meter thick wall of steel is very doable. A little bit about the onion core. So it's roughly 2.3 meters in diameter, and it's mostly full of water. It's of course heavy water. Heavy water is a really, really good moderator. And then you have a thorium blanket and you see how the blanket is constructed so that it encapsulates the whole reactor core. And that's really important because this way we optimize or minimize the leakage neutrons. Most reactors, especially fast reactors, they have neutrons flying out of the core. Like some fast reactor designs have half of the neutrons flying out of the core. And neutron economy is really, really important if you want to have a great fuel economy in a nuclear reactor. So how can it be great if half the neutrons are just lost out? With this kind of thorium blanket, we can get neutron leakage down to 2%. No reactor's ever been this efficient. And of course, in the blanket, we breed uranium-233 from thorium. Some people say, oh, you extract protactinium. No, we don't extract protactinium. We extract all the different uranium species in the blanket, and then we put them into the fuel salt. And the fuel salt, of course, being the orange colored channel in the middle, that is where the heat is produced. And of course, the heavy water is there to moderate or slow down the neutrons. So how can you have 600 degrees hot salt right next to cold water? Well, you need a little bit of insulation. We have roughly 1 inch of insulation between them. And that's enough because the majority of the heat in the water doesn't come from heat radiating from the hot channels to the cold channels. The vast majority, more than 90% of the heat in the water comes from slowing down the neutrons. So I mean, we need to cool the water anyway. So we only need a little bit of insulation, like roughly 1 inch, to make sure that the water doesn't boil. And of course, we have to cool the water all the time. So our reactor, if you look at a 1 gigawatt power plant, it would look something like this with an array of reactors in these cocoons. In this case, we would need 25 reactors for a 1 gigawatt plant and then some additional empty cocoons so that we can swap things around. And the whole idea with this power plant is that no humans go inside this building for 50 years. It's running for 50 years. Of course, you can go in there if you want to, but we don't want to have humans mess up things. So everything in there is remote controlled, like remote controlled cranes, remote controlled forklifts, and then somebody from the you could say operation room controls what's going on in there. That building produces heat, and then we transfer the heat through some pipes over to some buffer tanks, and then you can see there's a line of steam generators. So if you want to make steam, you can run a steam turbine or use the steam for some industrial process. So I said in the beginning, how can we construct a machine that can convert thorium into energy? And I think we are closer than ever to make that happen. This is one of our test reactors that are now running in Copenhagen. When I say running, it's heated by electricity and it's pumping the salt around. It's not fission going on or chain reaction going on yet, but we're getting close to that point. And here's a picture from inside where you see the onion core and some of the pipes and the heat exchangers and heaters and other things, pumps. So that was a lot of information, and I don't expect you to remember all of it. Of course, it will be available on video, so you can always watch this video or other videos on our YouTube channel. We try to come out with videos sort of every month or something, so there's a little bit new things. But I hope that you can at least remember these 3 things when you talk to your neighbor or your colleague next week. So because we've developed thorium energy to a new level, we can produce energy at a lower price than any other energy technology, including fusion or wind and solar or oil and gas. So we are not afraid of competition. We can beat anyone on price. We also know that nuclear energy, for the longest time, it has been financed and operated by governments, at least financed for the most part, or secured by governments. But we think this is going to change. We think that in the future, the nuclear industry should become a commercial industry. We don't want taxpayer money to run our reactors. Copenhagen Atomics will finance, build, own, and operate the reactors at a customer site. And we believe most of our customers will be customers that make commodities, such as ammonia, aluminum, other things, hydrogen. And And then we will operate our plant at their facility, but we will finance it, the capex up front, the capital cost of building it, and we will run it, and then we sell the heat to the customer on a long-term contract. And then the final thing I want to note is that the Copenhagen Atomics reactor is also capable of running on spent nuclear fuel. Unfortunately, it's a little bit difficult to get approvals to get some spent nuclear fuel and show that you can run on that. So we have postponed that a little bit into the 2030s to get up and running with that. We are really happy to see that Curio, for example, spoke earlier today, is working on that. In our reactor design, if you take spent fuel from a classical nuclear reactors, we can get 10 times more energy out of that fuel than what came out of it in the old reactor. So it's a significant higher, say, burn up or value coming out of spent fuel than first time it was used. And then we will store the fission products for the first, say, 50 or 100 years, so that the 90% of the radioactivity from the fission products has decayed away before we give the fission product back to the government or the state where the energy was produced. So we still want to take the fission products and give it back to the country in which we're operating. And of course, they have to accept that. That's part of the deal. But I think it's much easier for a country to get fission products that are already 100 years old and have very little radioactivity left in them. And fission products only needs to be stored above ground for maybe 300 years in total before you don't have to protect them anymore. So it's a very different way of looking at nuclear waste than how we look at it today from spent nuclear fuel. So that concludes my talk. I hope some of you have some questions.